In today's video, we study optimization problems. An optimization problem involves trying to optimize a certain quantity. That is, we wish to maximize or minimize this specific quantity. So in this video, we're just going to look at several examples. And by solving these examples, we will be able to develop a technique for solving any optimization problem. For our first example, a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other three sides. Given 100 feet of wire fencing, we wish to determine the dimensions that would create a garden of maximum area and then decide what that maximum area actually is. So to start off, let's represent the rock wall with this blue line. Then we'll use yellow to represent wire fencing. Right, we'll label everything, so we'll say y, y, and then down here we'll have x. And this is the area that we wish to maximize. Now we know that area of a rectangle is given length times width. The perimeter will be given as the sum of all the sides. So it'll be y plus x plus y. We don't need to worry about this here because that's a rock wall. It's not part of the wire fencing. So x plus 2y. Now that has to equal 100. Solving for x, we find that x is 100 minus 2y. So we can now write area strictly as a function of y, and it will be 100 minus 2y times y, or 100y minus 2y squared. We now need a domain. So what values can y take? Well, obviously y has to be larger than 0. And the largest it can be is 50, right? Because x has to be larger than 0. And so that means 100 minus 2y is larger than 0, and y must be less than 50. Now to find extreme values, remember we took the derivative and set it equal to 0. This gives us y is equal to 25. Now we have to determine, is this a maximum or a minimum? Well, we can use the second derivative test. A double prime is negative 4. This means that a double prime of that 25 is less than 0. So 25 does indeed result in a max. We plug 25 back in up here. That gives us x is 50, so the dimensions that maximize area is 50 feet by 25 feet. The maximum area is 50 times 25, which is 1,250 square feet. Next up, let's consider an island that is 2 miles due north of its closest point along a straight shoreline. A visitor is staying at a cabin on the shore that is 6 miles west of that point. The visitor is planning to go from the cabin to the island. Suppose this visitor can run at a rate of 8 miles per hour and swim at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? So let's say this point here represents the island. Now we know that it is 2 miles due north of its closest point along a straight shoreline, There's that, so that'll be 2 miles. And the cabin is 6 miles due west of that point. So the cabin will be over here somewhere. That is 6 miles. We're asked how far this visitor should run before starting to swim. We'll say right here will be the point where they start to swim. And we will call that distance L. Right, then this distance here is 6 minus the distance run. Right, this distance will be how far that they ran, which is x. Right, so we'll explain everything. X, the distance ran. L will be distance swam. Now, what do we know? Well, the time spent running is how far you run divided by how fast you run. Time swimming, same thing. It's how far you swam divided by how fast you can swim, which in this case is 3 miles per hour. Total time, which we shall call T, is time that you spent running plus the time that was spent swimming. Right, so this is the distance. This here is the value that we're trying to minimize. We need to express L as a function of x. Well, if we look, we have a right triangle. So 6 minus x squared plus 2 squared has to equal L squared. This means that L is the square root of 6 minus x squared plus 4. So the time as a function of x will be x over 8 plus square root of 6 minus x squared plus 4 all over 3. Domain, obviously x is going to be 0 as a lower bound, right? You could not run at all, or you could run the entire 6 miles to this point and then swim 2 miles. Right? It makes no sense to run past the point, because then you'd be going backwards. T prime, we get 1/8 plus 1 over 6 times times the quantity of 6 minus x squared plus 4, all raised to the minus 1/2 power, times 2 times 6 minus x times minus 1, that is all chain rule. Simplifying this, we get an 1/8 minus 6 minus x all over 3 times that square root. Set that equal to 0. This would mean that 6 minus x over 3 times that square root is equal to an 1/8. Cross multiply. Now square everything. So 64 times 6 minus x squared is equal to 9 times the quantity of 6 minus x squared plus 4, and that is 9 times that quantity squared plus 36. Now isolate the 6 minus x squared. So subtract that. Divide by that 55. Take the square root. And finally, subtract 6 and multiply by a negative 1 because that is a negative x. So actually, let's do that in 2 steps. Negative x will equal 6 over the square root of 55 minus 6, or x is, this should be plus or minus, I apologize. So this should be plus or minus. X will be 6 plus or minus 6 over the square root of 55. Well, take 6 over root 55. That's clearly a positive number. Adding it to 6 is going to make it larger than 6, which we can't have. So the only point of interest is 6 minus 6 over root 55. Now, to verify that this is a min, you would use the second derivative test. This will be left to the viewer to verify that that does indeed give a minimum. And so what we say is the visitor should run 6 minus 6 over the square root of 55 miles before swimming. This will minimize the time. Now, let's look here. Owners of a car rental company have determined that if they charge customers P dollars per day to rent a car, where P is between 50 and 200, the number of cars N they can rent per day can be modeled by the linear function N of P equals 1000 minus 5P. If they charge $50 per day or less, they will rent all their cars. If they charge $200 per day or more, they will not rent any cars. Assuming that the owners plan to charge customers between $50 per day and $200 per day to rent a car, how much should they charge to maximize their revenue? All right. Now, revenue. Is the price you charge per unit times the number of units sold. In this case, the price you charge per car rented times the number of cars you rent. So this will be P times 1000 minus 5P, or 1000P minus 5P squared. And they are told us the domain. $50 to 200. Take its derivative. 1000 minus 10P. Set it equal to 0. This will give us that P is equal to 100. R double prime of P is negative 10. So this means that R double prime of 100 is less than 0, which means that 100 does indeed result in a max. Thus, they should charge $100 per day to maximize revenue. And finally, a rectangular box with a square base and open top and a volume of 216 cubic inches is to be constructed. What should the dimensions of the box be to minimize the surface area? And what is this minimum surface area? All right, so let's draw our box. It's not going to give me enough room. Here we go. All right, let's say this is x. Now it has square base, so this must also be x. And then we'll say this is y. Now, surface area of the box is the sum of the areas of each side. Well, we don't have a top, right? The top is open. So the bottom area is x squared. Then we have four sides, each of length x with y. So that'll be plus 4 times x times y. Volume of the box would be given by x squared times y. And we're told that has to be 216. Solving for y, we get y is 216 over x squared. So we can write surface area is strictly a function of x as x squared plus 4x times 216 over x squared. So x squared plus 864 over x. Now, feasible domain, obviously x can't be 0 or less. However, x could in theory grow infinitely large. So s prime of x is 2x minus 864 over x squared, right? So this will be 2x cubed minus 864 all over x squared. Since 0 is not in our domain, we can just set that equal to 0. This gives 2 times x cubed minus 432 is 0. So x cubed is 432, where x itself is the cube root of 432, which is 6 cube root of 2. Now if we take s double prime, we get 2 plus, what is that, 17... $17.28 all over x cubed. This would mean that s double prime of 6 cube root of 2 is greater than 0, and so this does indeed result in a min. Right? So dimensions of the box, we need to solve for y now. So y itself, remember we said was 216 over x squared. So 36 cube root of 4. And this winds up being 3 cube root of 2. And the dimensions. That minimized surface area is 6 cube root of 2 inches by 6 cube root of 2 inches by 3 cube root of 2 inches. And that actual surface area would be 6 cube root of 2 times 6 cube root of 2 times 3 cube root of 2, which is 36 times 6. And that is 92? No, 192 cubic inches. And that concludes our look at optimization problems. The next video in this lecture series, we will be looking at the area problem, which is our introduction into integration, which is the final unit of this video series. I will see you all in the next video.